Okay, a short time ago, but with all of the students missing, it seems like longer, we talked about Lenz's law, which dealt with inducing magnetic fields and electric fields. So when you have a, specifically when we saw when we had a changing magnetic field, which we had a magnet going towards a coil of wire, that coil of wire inside it would have an electric field and a current induced that would create its own magnetic field to try and repel the change that it, or stop the change that it saw. And that essentially is Lenz's law. We are going to extend that today, thanks to Jacob and Sam for trimming all of these for me, to an extremely useful device that all of you probably have 3 or 4 of, and you know where they are at any time. Namely, those are transformers. This is just an AC transformer, but the ones that you use for chargers have some similar electronics in them. And here is what we're going to do. We're going to have one source on this. This is going to become our our magnetic core. This is iron. We're going to have a source on here. So we're going to take one of these little coils and put it over one of the rods. The other is going to be sort of an output. And if you are familiar with the green boxes that you often see outside of homes that sometimes buzz, the electrical boxes, the largest ones, that's essentially this is essentially what's inside them. They buzz because as these are changing the current, they tend to vibrate a little bit. I don't think we should experience any of that because I think this stuff is not strong enough. What I want you to do today, though, is set up one of these as your source side. And by what I mean by that is you're going to connect 2 of these parts to a power supply, but now we're going to use the AC part of the power supply. And let's review why. If you had a magnet sitting inside your coil, how much current did you get out of the coil?
Nothing when it just sitting there.
Nothing when it was sitting there. That's because when you don't, in the absence of a changing magnetic field, you don't get the resulting electric field. So if we hook this up to just direct current, what we're used to using, like batteries, where it's going one way, we would get a little spike as it went from nothing to whatever that current built up to. And we'd get a little spike of magnetism going around, but then as soon as that was steady, while this would still be magnetized like we saw in our electromagnets, there would be no changing field. So we wouldn't get anything on our output. But you will see something if we use an alternating current, because that's constantly changing. The electrons are being pushed back and forth 60 times per second from an outlet, for example. And the voltage is actually a sine wave, both above and below 0, so it's switching directions and whatnot as well. And that allows us to have sort of a continuous change here, continuously changing magnetic field that will be within our iron and going from our source over to our output. So
you plug both of them into one?
There is, if you open up your packet to lab 3G, there is a diagram there that I'll refer you to. One side, your source side. So how did we draw shorthand for a battery or a DC power source? Short line and long line, right. So we'd have something like this. So wire, short line, or long line, short line, and then this would be our power source. That's what a DC power source looks like. Over here on the far left with that little tilde in it, that is an AC power source, kind of to represent the sine wave. What I want you to do is our primary coil, or sort of our input coil, I want you to hook up an ammeter so you can measure the current going through there. These are pretty thin wire, so I think we're going to limit ourselves to, let's say, 1 amp. Don't go over 1 amp, because we run the risk of overheating the wire and burning it through it. And that's a pain. Also want to measure the voltage and record that across the coil. so across our source. When you're doing both of those, since we're dealing with alternating current, we have to use the little parts of the multimeter that also have the alternating current symbol, the little tildes next to them. So when we're measuring current, that means down in the lower left, and voltage is down in the lower right in both red and green, but not in the ones that we're used to using for DC. Then on the other side, our secondary coil, I want you to put both an ammeter. Now this ammeter is sort of completing the circuit, like what we did with the large coils and the actual magnets that we were moving around last time. And I also want you to record the voltage. These aren't going to be perfect or really, really efficient even transformers like we'd see in the actual electrical field or electrical practice. But we still should be able to see a relationship between what we put in and what we get out. Now, a couple points of caution here. One, we only have 2 sets of these coils, so you'll have to share. I want you to try several different measurements with differing coils on the 2 sides. I wouldn't be opposed if you had one time that they're the same number of coils on each. That might be interesting just to see how much we'd lose, even though that's, sort of the closest thing we would have to 100% where it should make 100% transfer. But we've got 8 coils in each set, so you can change off there. Some of these, you'll notice, because I used as large of center core as possible, some of these brass thumb screws here, or the nuts, might come into contact with that. And we want to make sure they don't, because then you could just short straight across and you wouldn't have any electricity going through the coil at all. So if they do touch at all, you can unscrew this larger portion and just set it aside and put it back when you're done. You can clip to this little post standing up, and then you wouldn't run as much risk of connecting to the center, to the iron core. The second thing, or I don't know, third, I lost count. The other thing is that this tells us how much wire is on it. So this says 200 centimeters, but it does not tell us how many coils. So you have to figure that out. Start with the smallest one. Well, actually, maybe we'll do this together, because I think I have it written down over here. No, you might be on your own. You really might be, which isn't tough, but we're going to start with the 40 coil. Yeah. 40 centimeters here has, let's count, 1, 2, 3, 4, 5, 6, 8 coils on it. 7 to 8. But the other thing with this is that if I measure the approximate size, I can get that each side of this, it's a square, and it's about 1.2 centimeters. So if we have 1.2 centimeters on a side, that means 4.8 centimeters circumference. And we have 40 total centimeters of wire. How many coils should that be? And that will allow you to estimate pretty carefully when we get up to 2,000 centimeters how many coils are going around this without having to try and count them. It's a little joke, because that's a lot. And my recollection is that it's going to be, it's going to be like 7.8, 7.7, something like that. So you can estimate then based on that going around. Okay? So I want you to do several different trials. You clear on what is going on?
Yeah.
You'll be able to put it together. Yeah.
In the diagram, does the tilde just represent the AC power supply?
What the tilde is the AC power supply. Yep.
Then so the A is the ammeter.
Yep.
Then you hook one end of that into the voltmeter.
Right. So when it's got a power supply, you actually need to measure the electrons going through. So you'll put it as more or less as one of the connecting wires.
Mm-hmm.
And that's why we'll get the power supply, ammeter, then your coil, and back. And then you'll put your voltmeter off to this side just to measure the voltage. But on the other core over here, if we just have it like this, there's nowhere for those electrons to go. So it's a very, very inefficient transformer, and you don't get much motion. We need a circuit over on that side as well. And the easiest way to do that circuit is just to complete it with the ammeter.
Is that AC or DC?
AC.
It's also AC. Yep, because it's constantly changing, both sides will be AC. A DC power converter, so one like a charger, is quite different. It needs electronics usually to do it well anyway. Okay. Okay, let's go to it. This is a pretty quick lab, I think, so we'll be able to finish easily and then probably chat about it later.